Thank you for having me here for this talk. As Greg was saying, you should feel free to ask questions now or later, and I can put my email here if you want to ask them offline. That's fine. I'm going to spend the next 45 minutes or so telling you about the secret life of quarks. So I'm going to tell you what quarks are, and I'm going to tell you why they're extremely weird things. They are very, very quantum things, and the way they behave is very counterintuitive. But over the last 40 to 50 years, we've managed to really piece together what the reality at the scale of quarks is. So to set the scale for this talk, I have this picture here that really shows, okay, we're living up here at kind of macroscopic scales, and we go down beyond microscopic, beyond molecular scales, down to atomic scales, where we have a cloud of electrons zooming around a nucleus. The nucleus is made of protons and neutrons, and those protons and neutrons have substructure themselves. So it's really this substructure that we're going to spend today talking about. And so this is a very simple picture of what a proton looks like. It's not just a single thing, it has things inside it, and those things go by the name of quarks. And this, as I hope you'll see in this talk, is a ridiculously simplistic picture of what a proton looks like, that it just has these three things inside it. It's, in fact, much more complicated. So we're down at scales. I should have put a unit on this ruler, actually. This is a nice logarithmic ruler, and it's in units of meters. So we're talking about here down about what are called femtometers, so 10 to the minus 15 meters, so extremely small. The dynamics that happens here, these things inside the proton are moving at essentially at the speed of light. So really the dynamics that's happening here, you can take this distance scale, 10 to the minus 15 meters, and ask how long does it take a quark to go across this nucleus, this proton or a nucleus, and it's traveling at the speed of light, and that gives you basically 10 to the minus 25 seconds. So these are extremely fast moving things, extremely short time scales that are involved, and that's the world we're going to talk about today. So this is the world of the standard model. This is really the way we understand matter at its shortest distances. We have a theory of that, and this is called the standard model. And the standard model is something called a quantum field theory. So I imagine most of you have heard of quantum mechanics. So quantum field theory is sort of a generalization of quantum mechanics. And this particular example of a quantum field theory is called quantum chromodynamics, or QCD, plus another quantum field theory called the electroweak theory. And what these theories describe is really everything we see around us. So they're made up of particles. So that's the outer rim of this nice pie chart here. So we have various types of quarks, so up quarks, down quarks, strange quarks, charm quarks, bottom quarks, and top quarks. And the order I went through that is kind of perverse, but is really related to how big those quarks are. And then down the bottom we have what we call the leptons. So we have electrons and neutrinos, and then various cousins of electrons called muons and taus. Those particles interact with various different forces. So there are electromagnetic interactions. These are governed by the photon, which we have the symbol gamma for. There are the weak interactions, so the W and the Z bosons are telling us about weak interactions. And then the strong force, or QCD, is the interactions there are determined by gluons. These are the things that hold quarks together. That's why they're called gluons. So as well as that, I'm sure you've heard recently that the Higgs particle was discovered about 4 years ago now. And this Higgs particle, what it does is it gives mass to all of the particles in this chart here, except for the gluon and the photon. Those particles remain without any mass at all. But the Higgs provides the mass for all of these. However, it doesn't provide mass for everything in this room. That actually predominantly comes from the strong force, from QCD. So what we're going to do today is really focus on QCD. So we're going to talk about quarks and gluons, because those are the only things that participate in the strong interaction. Okay, so the first thing that you can learn about quarks is that we never see them. Okay? So when we build very, very large particle physics experiments, we try and look at the smallest scales that we can, and we try and probe nature at its most fundamental level. And we get building very complicated and expensive particle detectors. We get, in the 1970s at least, we got pictures like this from what are called bubble chamber experiments. And these lines here correspond to a particle moving through some region of, in this case, a superheated liquid hydrogen, and as it goes through, it basically forms little bubbles, and that's what this is. And then you can take a photographic image of those. So each of these lines corresponds to some particle moving through the region that this camera was looking at. So this was in the 1970s. Nowadays, we have the Large Hadron Collider in CERN, and there the experiments that look at the shortest distance interactions are even more complicated. This is the CMS experiment, and this is basically a computer readout of what the CMS detector sees as there is a collision of particles. Each of these lines corresponds to a reconstruction of where the particles came after the two protons were smashed together. However, none of these lines is a quark. Okay? Yes?
Scale of the photo on the left and scale of the photo
Right.
on the right.
So the scale of this one here. So this is basically a picture of the entire CMS detector, which is something that is about the size of this room, actually, completely filling this room, the CMS detector, maybe even a bit bigger. And yeah, so this blue region is that. The actual physics that we're really interested in, the very microscopic physics, is happening right at this point here, and then the particles are streaming outwards. And the detector itself is big, but everything is really focused down on this tiny little region. So over here, this is somewhat smaller. This region, so this was done, in fact, this experiment here happened before I was born. So I would say this is of order a meter scale. Basically, these the type of detectors, they were a big tank of liquid hydrogen that was heated up by using a piston that basically made it go supercritical, so that if something came through it, it would basically form bubbles. Okay? And so you have a big tank of liquid hydrogen. Making it even bigger is pretty dangerous because hydrogen has the problem that it burns. So really, this kind of technology turned off pretty quickly, and we use a very different technology in current detectors. Sure. Okay, so yeah, as I was saying, none of these lines are actually quarks. Okay? What they are is either leptons, so the electrons or muons, or they are complicated combinations of quarks. So because the strong interaction is very strong, what it does is it takes quarks and gluons and kind of clumps them together. And all we see is these what we call bound states of these things that are stuck together. And over time, we've seen many, many, many different types of these bound states, many hundreds of them. Okay? And in fact, every 2 years, what's called the Particle Data Group releases a book, which is about 1,500 pages now, that is a catalogue of all of the particles that we've seen and all of their properties. Okay? And this is the guide to this zoo of particles. So one of the triumphs of modern physics, or physics in the 1960s at least, is that this zoo of particles, many hundreds of them, were able to be classified in a much simpler structure. And so this was done by Murray Gell-Mann and various other people. And this classification of all of these particles was based on thinking that the protons and the other particles, so pions and neutrons and kaons and things, these were all made up of more fundamental objects. And these are where the name quark first came from. And the way this classification works is that all of these hundreds of particles, you can think of them in two categories. You can think about mesons, which are a combination of a quark and an antiquark, and baryons, which are combinations of three quarks. So just as one example, we have what are called the hyperons. So these are baryons, and you can see two particles, which this is the proton and this is the neutron. So these are ones that are probably familiar. But they come along with 6 other particles. There are sigma baryons, lambda baryons, and then these Xi baryons, which are commonly called cascade baryons. So what L.e.n.r and others realized is that these particles, say for example the proton and neutron, are very similar. So the mass of the proton and the neutron are almost the same. So the mass of the proton in kilograms is 1.672622 times 10 to the minus 27, and the mass of the neutron only differs in this fourth digit. Okay, so these are very close to each other. Similarly, the three different sigma baryons all have masses that are very close to each other, and these two have masses that are very close to each other. And then if you look kind of not along the rows, but along these diagonals of this picture, each of these particles have electric charge 1, these have electric charge 0, these have electric charge minus 1. So there's a lot of symmetry in this arrangement here, and it's really this symmetry principle that led L.e.n.r to actually be able to classify a very complicated book of stuff into much more simpler units. So we'll come back to these neutron and proton masses in a little while. I just want to convert them to units that are more convenient for particle physicists. Really, these units here are basically kilograms, but they're called mega electron volts over c squared, and these are just units that we more commonly use. So yeah, in terms of this, there is a still this small difference between the proton and neutron mass. And I will come back to this. Okay. So, well, I said at the start that a proton was not this very simple picture of three quarks, and then I just told you, well, protons are three quarks. Well, it's sort of right and it's sort of wrong. So let's try and ask this question, and we can actually do this using experiment. And so to do that, I need to introduce something, and this is called a quark distribution function. Okay, and I'll introduce this very slowly, I hope. So this is something q of x. Okay, it's a function of how much momentum a quark inside the proton is carrying, and we write it in terms of a momentum fraction x. And so x is going to be something, if a quark is carrying all of the momentum of the proton, it'll be 1. If it's carrying a tiny bit, it'll be almost 0. Okay, so x goes between 0 and 1. And what q is going to tell us is if I look at a proton, how likely is it that I do an experiment and I see a quark inside there carrying a particular fraction of the momentum. So let's think of an analogy for this, and it initially is kind of looks like a bit of a silly analogy, but it's actually not too far from a good analogy. So here we have a fishbowl with a bunch of fish in it sitting on a skateboard, okay? And so if we give it a push, it will start moving. So we're going to think of this as our proton, so I'm going to call this our proton momentum. So if we have this moving with some velocity this way, then momentum is just the product of the mass times velocity, right? And so this fishbowl has momentum in this direction. And what we really want to ask is, how is that momentum made up of the components of this fishbowl system? Okay, so this fishbowl is not just one thing, right? These fish are going to be moving around inside the fishbowl. So what I'm going to do is basically neglect all of the actual water in the bowl and just talk about the momentum of the fish. So let's say this fish here was swimming in this direction, inside the bowl, and then we make the bowl move. Okay, so now this fish is going to be moving quite fast in this direction. And so it's going to have a significant component of the momentum of the whole thing is going to be because this fish is moving this way. So we can write this as saying that this fish has a momentum, and really I only need to talk about momentum in one direction here, so I'm just thinking about going across the screen. So the momentum of this is some fraction of the total momentum. Call it x1, okay? And we can do the same thing for all of these other fish. This guy's swimming backwards, so his momentum is, he's swimming this way, but moving this way even faster, so he's just got a little bit of momentum in that direction, okay? But now we've really broken down the momentum of the whole system into the components of it, okay? And if you think about it, you'll see that, okay, if this is all of the constituents, and remember I'm neglecting the water, if this is all of the constituents, then all of these momenta should add up to the total momenta, right? And what that means is that sum over all of these x's, x1 plus x2 plus x3 plus x4 plus x5, has to be 1, okay, so that we get the total. Okay, so we can do this. We can do this little experiment once. We can basically take our fishbowl, set it moving, and then look at what the fish are doing. And then we can do it again, and the fish will be doing something else, right? And we can keep doing it many, many times, and we'll get basically a distribution of what fish like to be doing in fishbowls on skateboards. Which, okay, not a question that you would normally ask, but that's what we're doing. Okay, and so that lets us make a histogram. So basically what I'm going to do is say, okay, this guy has x1, maybe he's got x1 of, say, 0.6. Okay, he's carrying quite a lot of the momentum. So in my x range, I'm going to say around 0.6, I count 1. Okay, and then I take the next one, and he's maybe 0.3, so I put something in this column. And then I keep doing it, and I do it over many, many versions of this fishbowl, and I basically build up this histogram of just how many fish do I find carrying 60% of the momentum, or how many do I find carrying 10%? And I build up this picture. And then what this function q of x is basically the thing that in the limit that I have many, many copies of this and do a large statistical sample, I will map out some function q of x. Okay? So q of x is really telling us if x is 0.3, then that means that, well, quite a lot of those fish are carrying 0.3 of the momentum of the bowl in this case, but really I mean proton. Okay? Are there any questions about this? No? Okay. So what we want to do is do the same thing for a proton. Now, okay, protons are different than fish bowls, obviously, and so to actually ask the question of how fast the constituents if the proton are moving, we have to do much more complicated experiments. Before we get to those experiments, one thing that we can ask from this function q of x is how many quarks there are in a proton, right? I've just told, oh no, I have to redo, whoops, I have to go back. No, I've gone back too far, sorry. We've just built this histogram, and what this does tells us that this number of fish inside the fishbowl carry a momentum fraction 0.3, right? So if I want to know how many total fish there are, I should ask how many are carrying 0.1, how many are carrying 0.2, how many are carrying 0.3, and so on, and just add them up, and that'll tell me the total number of fish. Okay? So what I want to do is calculate that sum. Now, x can take any value. It doesn't have to be 0.1 or 0.2. It could be 0.11379, right? And so instead of a sum, we have what's called an integral, but really you should just think of this as a sum over all of the possible momenta that can be carried. And so if we just sum them all up, and over the range 0 to 1, which is the allowed values that x can take, we'll get the total number of fish, or now the total number of quarks inside a proton. Yes?
In your analogy,
yep.
It's obvious that there is a surface to the fishbowl.
Yep.
What's the surface to a proton, and what governs it?
Right, so the surface to a proton is really set by QCD, by the strong interaction. Basically, as you try and take a quark outside it, you'll see that it gets pulled back in. It's basically everything confines itself to some little region. And it's really through the fact that these quarks are talking to each other by exchanging gluons between them. And they're glued together. So there is no physical boundary, but just everything keeps together. Okay, so in order to actually calculate this, we need to know what q of x is for a proton. So we can't use that analogy anymore. We have to go and do what are called deep inelastic scattering experiments. So we need to go to a big particle physics accelerator and do the following thing. So we take a proton, and we can think about this sitting at rest as a target in this experiment, and then we take a very high energy beam of electrons coming in, and they interact with that proton target by sending off a photon and knocking something in here. Okay? And they get scattered off. And by measuring how they're scattered, you can actually learn about this quark distribution, q of x, inside the proton. So these experiments were first done in the late 1960s at Stanford, and they really set the stage for understanding the structure of the proton. So in this figure here, I'm showing this distribution q of x, and I've put a factor of 2 here. Because I also wanted to show not just this distribution of quarks, but also the distribution of antiquarks. Okay? And if I didn't have this factor of 2, these would be on top of each other and you couldn't see anything. Okay, so I've just offset them a little bit. So here we have this as a function of this x variable going from 0 to 1, but again I've made this a logarithmic scale, so 0 is infinitely far off that way. And this is just these distributions. And in fact, these lines here have error bars on them coming from their extraction from experiment, but they're very precise, in fact. So what this tells us is that, well, out here, so if x is, say, 0.5, there are very few quarks in the proton carrying half the momentum. Okay? If x is 0.001, so here we are carrying a 0.1% of the momentum of the proton, well, there's actually a substantial number of quarks that carry that momentum. Okay? Similarly, with the antiquarks, you also find that there are quite a lot of them carrying very small fractions of the momentum. Now, we can do these experiments and map this distribution of Q of x out, and we actually find that it has the following form. So I don't want to scare you with this formula, but it basically it goes like x to the minus 1.2. So as x gets very small, this is basically 1 over x, so that gets very large. Okay, so that's why this thing is going up very fast as we go towards x equals 0. And then as x goes to 1, well, this term gets very close to 0, and so Q of x goes to 0. Okay, so it's in fact, fairly simple form. But what it means, and for those of you that remember integration, or did integration, you can think about this function and say, well, this is actually something that when I try and integrate it, try and count all of the area under these curves, it's actually going to be infinity. Okay? And what that's telling us is that there are an infinite number of quarks inside the proton, not 3. Okay? You can look at this distribution of antiquarks as well, and that basically has a very similar form. And, well, that also, the total number of antiquarks inside the proton is also infinite. So that seems a little odd, because I told you before there were 3 quarks, so what am I talking about? Well, to piece that together, what we need to do is just think about this function a little bit more. And I'm going to replot it, but I'm going to plot not Q of x, but basically x to the 1.2 times Q of x. So that will make something that doesn't explode as we go to x equals 0. Okay? And so things look much nicer there. So this is Q of x, or x to the 1.2 times Q of x, and x to the 1.2 times the antiquarks. And now we actually see there's quite a difference between the two of them. Okay? And what we can do is actually say, okay, both of these become very, very large as we take x goes to 0. So, but in fact, they become large in exactly the same way, which is why these two curves come together here. So as we go towards 0, these become identical. And so, in fact, that region, if we ask not about the number of quarks and the number of antiquarks separately, but ask the question, the number of quarks minus the number of antiquarks, then that infinity will actually cancel between these two things. And so it's, in fact, the number of quarks minus the number of antiquarks, which is related to this area here between these two curves, which is a perfectly finite thing. This is 3. Okay? And so the proton, okay, when we say there are 3 quarks, we really don't quite mean that. We mean, on average, there are 3 quarks inside the proton. Okay? But really, it's much more complicated. So I can make a quick analogy with quantum mechanics. So I'm sure many of you have heard of Schrödinger's cat. For those that haven't, this is a thought experiment that Erwin Schrödinger came up with, where we take a cat and put it in a box with a radioactive source, which is a very quantum thing, and will decay or not. If it decays, it will force this hammer to smash this vial of nasty stuff that will kill the cat. Okay? If it decays. But we don't know if it decays. So we make this up, we close the box, and we say, well, what state is the cat in? And either this thing decayed or it didn't. Okay, that happens all the time. Okay, either it decays or it doesn't, and so either the cat is dead or not. But we don't know because we haven't opened the box, right? And so we think about this cat from outside the box. It's both dead and alive. So quantum mechanically we say we have a superposition of a live cat and a dead cat. And that's the state of that cat that we know until we open the box. When we open the box, we see it's either dead or alive, right? But this is really the state it lives in quantum mechanically in the meantime. So now let's turn to the proton and ask what Schrödinger would think about a proton. So he would not think that it's 3 quarks. Okay? It's really much more complicated. It's 3 quarks, but it's also, or 3 cats, sorry. It's also 4 cats and a dead cat, or 5 cats and 2 dead cats, and so on. Okay? So this is really the difference between quantum mechanics and quantum field theory is actually that even the number of cats in this box is not fixed anymore, right? It's kind of pretty weird. Okay, so now let's talk about the quarks themselves, because they're even weirder than protons. So what is a quark? So this is kind of complicated, and it really depends on how you ask the question, how you look at it. So we can do a little another thought experiment where we take 2 experimental physicists. I'm a theoretical physicist, so I like doing thought experiments using experimental physicists. But let's do this. So they're both experimental physicists. So Zach makes a particle accelerator, and this is a picture from a famous particle accelerator that was at Lawrence Berkeley lab. It's now decommissioned. And he does these deep inelastic scattering experiments. And so he learns something about a quark inside a proton. Okay? So this probably happened in the 1980s, and now Alice comes along much later in the 2010s and builds a much larger accelerator. This is now the LHC at CERN in Switzerland, and does the same kind of experiments, but with much, much higher energy collisions. Okay? And she looks at the same proton, and she sees not a quark, but actually a quark and 2 gluons. And remember, gluons are the things that carry the force between quarks. Okay? So, how does this make sense? Well, I need to tell you one thing first. So the reason we try and build bigger and bigger particle accelerators is because the scales at which we can probe things are inversely related to the energy with which we do collisions. Okay, so the LHC is a much, much higher energy collision than the other experiment I showed you. And so this comes from this relationship here, which is basically tells you that for a photon, the energy of a photon is inversely proportional to the wavelength. So if we think about light, light comes in many different wavelengths. So red light is a longer wavelength than blue light. And so the energy of a blue photon is actually somewhat higher than that of a red photon. And if we go beyond the visible spectrum, down here you have X-rays and then gamma rays, which are getting shorter and shorter wavelengths and getting higher and higher energies. And if you think about taking some object here and taking this wave and impinging on it, if the object has structure that's smaller than the kind of undulations in this thing, you're not going to see it. But if you come down here where the undulations are much faster, you'll be able to resolve that smaller structure. Okay, so by going to higher and higher energies, we're able to see smaller and smaller details of the picture of particle physics. Okay, so we can then think back to these 2 experiments. So here we are with Zach's experiment. So here this is meant to be the proton. Zach is working at some relatively high energy, E1, okay, and he sees a quark carrying a particular fraction of momentum in the proton. We can go to higher energy, and let me do both of these, and we can go all the way, we can go to a sort of an intermediate energy, and here what happens is that we've gone to a higher energy and we resolve structure inside of this quark. And that structure is actually in terms of a quark and a gluon. Okay, so there are quarks and gluons inside quarks, which is sort of a little counterintuitive to say the least. So what happens though is that this quark here was carrying momentum fraction x. Now this quark is carrying less momentum, and this gluon is carrying some momentum. And the sum of them is still the original momentum of that quark, or momentum fraction, I should say. Now we can go to Alice's experiment, which is at an even higher energy, and she resolves even more structure inside here. So she sees a quark and not just one gluon, but 2 gluons. But again, all of these momenta add up to the same as this original momentum. So what we see what we think of as a quark at one resolution scale, so one energy scale that we're probing the system, or a length scale that we're probing at, is actually a more complicated thing when we go and look more closely. Okay? So now our picture of Schrodinger's proton gets even more complicated. So we don't just have cats and anti-cats, or live cats and dead cats. We also have dogs, and these are the gluons. Okay? So the picture of the proton gets more and more complicated. Now, amazingly, we have a theory that actually tells us exactly how what we see should change. And so this is QCD, quantum chromodynamics, and it predicts this. And it predicts it in a fairly complicated way. There's a set of equations called the Dokshitzer-Gribov-Lopatov-Altorelli equations, which, given their long name, they probably are pretty formidable equations, and indeed they are. And this is Mr. Lopatov here, who, when he's working at blackboards, never erases anything. He just keeps writing over the top of stuff. Makes it very hard to follow what he's doing, but he develops some pretty amazing things. So what these equations actually do is take us from the quark distribution function measured at one energy scale and allow us to work out in a completely predictable way what it will be at another energy scale, and then to another energy scale. So this picture that I had, this picture that I had here is actually completely calculable and under the control of this guy and friends. Okay? And it's also completely verified by experiment. So this is a pretty complicated plot here, so I want to explain it carefully. So this is a plot of this quark distribution function, and this function is a function of the momentum fraction and also the energy scale. So what's plotted here is the energy scale, and then each of these little curves corresponds to a particular value of x. Okay, so large x is down here, and small x is over here. We don't need to think about all of these, but let's just focus on, say, x equals 0.008. And here we have a bunch of data points and a curve with an error bar on it. And the curve is actually a prediction from these Dirac evolution equations that if you measure the quark distribution at some particular energy scale, you can predict exactly what it will be at other scales. And then you can do your experiments. You can do an experiment here, you can do an experiment at this higher energy, or you can go to the LHC and go to really high energies, and that's what the data here correspond to. And so these predictions of QCD are completely verified by this data here. And so this is actually probably the most compelling piece of evidence that QCD is really the theory of the strong interaction. Okay. Yes?
How are these evolution equations derived? I mean, are there some basic principles?
Yeah. So let me come to that in a second, actually, because I won't derive them, because. But I will tell you a little bit about how they're derived, what kind of the mathematical way we get to them is. Okay, so this was really talking about just the shortest distance structure of the proton, asking what the quarks are doing inside it. But really, we should, if we think we understand reality, we should be able to describe the proton itself, everything about it, right? We should also be able to describe more complicated things. We should be able to describe nuclei, and we should also be able to describe macroscopic things like neutron stars, because basically the same physics that determines the structure of the proton, determines how protons form nuclei, determines what happens in neutron stars. Okay, there's also gravity involved here, but let's ignore that for now. So yeah, we really have a much more complicated task ahead of us than just trying to understand this very short distance structure inside the proton. We really have a much bigger thing to do. So the simplest question that we can ask that is not about quarks is, well, what is the mass of the proton, or in this case, the neutron? So you might think this is a pretty simple question to ask, but it's basically taken 35 years of hard work and lots of people working on this and lots of big computers to actually work out as theoretical physicists what the value of the neutron mass is. So the timeline for this is basically this theory, QCD, was discovered or invented in 1973. Very soon after that, a technique called lattice QCD was invented or discovered. And so this is what's actually going to let us solve this problem. And I'll tell you a little bit about this. And then people tried to calculate things like what is the mass of the neutron. And so the first actual attempts to do this were in 1979, but they were very far from being able to do anything that would tell you anything about the neutron. And it's taken from there until 2008, until the first what I would call complete calculation of the mass of the neutron from the fundamental physics that we think describes the neutron actually happened. And so this appeared in Science in 2008. So we'll come back to this in a little while. Unfortunately, at least unfortunately for theoretical physicists, there's a thing missing in this timeline, is that in 1932, James Chadwick, in the paper where the existence of a neutron was first demonstrated, measured the mass of the neutron to much higher precision than we'll ever be able to calculate it from QCD. Okay, so a little humbling for theoretical physicists. Okay, so why is this so hard? And this is really because the QCD is the strong force, and the interactions between quarks and gluons are very strong. Okay, and so we can contrast what happens when we take electrodynamics. So we take a positive and negative charge. So say an electron and a proton, and forget about the proton has structure to it, but just say take a positive and a negative charge. Well, they interact through exchanging photons, but they do it in a way that if I take the positive and negative charge apart, the force between them, which is attractive, gets less. Okay? And it falls off, in fact, like 1 over the distance squared. So if I start with them here, move them twice as far apart, the force they feel is down by a factor of 4. And so I can take them off, and it gets less, and it gets less. So I can pull them apart. QCD is quite different. So the analogues of a positive-negative electric charge in QCD are a quark and an antiquark. And because the force-carrying particles in QCD, which are the gluons, are very different than photons, they actually interact with themselves, not just with the charges of the theory. And so what happens is that all of the gluon structure likes to sit between these two quarks. It doesn't go off like these lines tell you that the photons are kind of going off everywhere. For gluons, they really stay together. And so if you think about this, well, you can calculate what the force that is required to pull these quarks apart is going to be. And it basically becomes independent of the distance. So as we try and pull them further and further apart, we have to pull just as hard to move things away. And so if we want to take this quark and the antiquark, and we want to get just one quark, we have to take this antiquark all the way off to whatever is in that direction, off infinity. And each time we move it, we need to do the same amount of work. So we move it 1 meter, we need to do some work. We need to move another. So to get it way over there, it essentially costs an infinite amount of energy, which is why we will never see a single quark by itself. It would cost infinite energy to do that. Yes?
So, but when they're really close,
yes.
it's easy.
That's
Yeah.
So right. So yes. So that's what I will explain next.
Oh,
okay. So this is really this picture here, which is a Nobel Prize-worthy picture, and a particularly important Nobel Prize here. So this is David Gross and Company's Nobel Prize in 2004, was really the prediction that well, if I go back here, was really the prediction of what should happen down here. Okay. So what's shown here is the interaction strength between these two quarks as a function now of energy, not distance. But remember, energy is inverse of distance. So high energy means very short distance, and low energy means long distance. Okay? And so what you see is that the strength of the interaction is going down as we go to high energy. Okay? And as you saw, that's what's happening down here. The force between things as they get very close to each other, closer than the size of the proton, that goes away. Okay? And that's this going out here. And I should point out that the curve here is the prediction of quantum chromodynamics, the prediction of Gross, Politzer, and Wilczek. And the data points correspond to various experimental ways of measuring this strength of interaction. Okay, so this is actually very nice. So if this becomes small, we can think about some quantity that we want to calculate, which I call O, and think about it as an expansion in powers of this strong coupling alpha S. So if alpha s is 0.1, well, this term here is small compared to this one, and this one is even smaller, and so on, right? And so if I want to calculate this quantity, whatever it is, to some given level of precision, I can basically say, okay, well, that's enough. The next term is going to be 10 times smaller, so I can forget about it. Okay? And so this is what's called a perturbative expansion. Basically, you're doing an expansion in a small number. And this is actually, in fact, how these Bochitzer-Gribov-Lapatov-Altorelli-Parisi equations are derived. They're something that works at very high energies and works because the strength of the interaction is turning off. So unfortunately, the other end of this curve is that as we go to low energies, and so 1 is basically the mass of the proton in these units, this coupling strength becomes very, very large. And so doing an expansion here is basically an expansion in something that is basically 1, and so it's not an expansion at all. So such a method is just not going to work. So this is really where things stood for a long time. So we've been able to do many, many calculations at high energy and basically verify QCD by doing these calculations on pen and paper, doing Feynman diagrams, which you've probably heard about. But at low energies, this is just not going to work. So we did a new tool. That new tool is lattice QCD. And I'm not going to tell you technical details about this. I'm really going to think of it basically as a black box, although we'll open it up very briefly because it looks kind of cool inside. And let me just tell you why it's called lattice QCD and why we have these nice pictures here. So it's really just a way of dealing with these quarks and gluons when the interaction between them gets very strong. Okay? It's called lattice QCD because in order to calculate things mathematically, we have to think about not a continuous space-time, we think about a discrete set of points. So we only think about things that could exist here or here or here or here, not anywhere in between them. Okay? And so we have what's called basically have a four-dimensional space-time grid of points where we define our equations and then we can solve them. Of course, reality is not this discrete system, but this is really the origin of the name lattice. It's a set of points. So now this picture here, or this animation here, and this is due to a person from the university where I got my PhD. This is a picture of one of the ways in which these quarks and gluons like to arrange themselves. So in order to actually do a calculation, what we need to do is think about what these quarks and gluons could be doing on this funny grid of points. Okay? And we have to think about all possible ways they could be arranging themselves and moving around and doing things. And this is a depiction of just one of those possibilities. So remember, I'm thinking about space-time here, so it's a four-dimensional thing. So this sort of three-dimensional volume rendering, the fact that it's changing in time, this is really just one of these configurations of what the quarks and gluons want to be doing. Right? And the colors mean something, but not relevant for what we want to discuss.
Is that at each point or the whole lattice?
Right. No. So you can see this grid here. So this is showing each point of this lattice. So you're basically asking what is the value of this gluon at each point in space-time. Okay. And the way we do this is the way we do calculations is by generating many, many ways in which those quarks and gluons could be arranging themselves and then doing averages over various things of those things to extract quantities that we want. The hardest part about this method is actually not doing either of these things. It's actually understanding what you've done by deciding that space-time is not continuous but is a discrete set of points. So what you have to do is then take this separation between these points off to zero, right, and understand how that happens. And here, I say we're going to average over many representative configurations, and in our calculations, many might be some number of thousands, but strictly speaking, the correct answer only emerges in the limit of the infinite number of these samplings of what quarks and gluons want to do. So understanding that limit is also very complicated, and both of these contribute to this being an extremely computationally demanding thing, which is why this has taken so long for this to be a problem we can solve. So it's basically taken 30 years of working out algorithmic and computational details of how you should do the calculations in order to be at the state we can do this. And remember, this is 30 years riding on the back of the Moore's law increase in the computational power that you can use, right? So computers have got exponentially better over time. In fact, our algorithms have got even more exponentially better over time, and it's taken both of these to get to a state where we can do proper calculations of these complicated quantities. So just to give you a scale for what we do, in 2015, all of the people doing lattice QCD calculations in the US used about 10 billion CPU core hours, which is kind of a large number. If you think about that, that means that essentially 1 million CPU core hours were running continuously for a year. And that happens every year, in fact. Now, of course, CPUs now have multiple different, maybe 10 cores in them. And so that means we actually only had 100,000 computers working on this problem continuously for a year. But that's what it takes to do these calculations. Okay? And these are some pictures of some of the very large computers that we use. Okay, so now I want to say one thing about how we calculate a mass, because here again is something where I think there's a pretty nice analogy we can make. And this is an analogy with dropping rocks into water. Okay, so if you think about dropping a rock into water, what's going to happen is that, well, the surface is going to change, and there's going to be a pattern of ripples coming out from where you drop it. And that pattern will depend on what the rock was, right? If I drop a tiny pebble, I'll get a small ripple. If I drop a rock, as you'll see here, a large rock off a bridge, there'll be a bigger response. Okay, so what we're going to do is drop a rock in here, and then I'm going to sit out here and measure how the surface of the water goes up and down as this ripple comes and passes through here. So here it is coming out, going up and down, and then up and down again. Okay, and so I want to look at that, and then I want to do it again. And so now I'm going to drop a much larger rock, and I'm going to sit the same distance away, and obviously the ripple that passes through the point the same distance away is going to be very different for this big rock, right? And so you can actually, just by measuring that response of the fluid that we're sitting in, you can measure about what the perturbation or what the disturbance you imposed on this system was. Okay? Yes?
When you're measuring that, are you going distance and time, how long it takes?
Yeah, and basically, what I want to do is think about sitting at some particular point. So here was the center. Let's sit, say, 1 meter away. And as a function of time, measure how the surface of the water goes up and down, right? And that mapping out that dependence will tell you whether it was a big rock or a small rock, essentially. Okay? And basically, in lattice QCD, to measure a mass of a proton or a neutron, we do the same thing. So we do it in a funny space-time lattice, and what we think about is basically taking a configuration of taking kind of the vacuum and then exciting it, and this is basically dropping the rock. And what we do to excite it is force it to create 3 quarks here. And 3 quarks have the right quantum numbers to make protons. And then I want to sit with my little measuring stick, measuring the height of the water, some distance, and I do it in time in this case, away from where I disturb the system. Okay? And what I want to do is move this measuring point forward and backward in time. And, okay, you could do something in space as well, but let's not worry about that. And the nice thing about these lattice QCD calculations is all I have to do is get the quantum numbers of this system right. I don't have to actually understand exactly what a proton is. The averaging over all of these configurations of the quarks and gluons actually puts all of the quark and antiquark pairs that really should be here and all of the gluons in automatically for me. Okay? So now what I'm going to do is basically, as a function of the distance t, have some correlation between the disturbance I'm putting in and the measurement I do, a distance t away. Okay? And by measuring that, I actually extract a response. So c is that response as a function of t, and it basically goes down and up in this case. And it depends on the mass. So if the mass was 0.05, it goes down like this. If the mass was 0.2, it goes down like this. And so by calculating this, what I call a correlation function in lattice QCD and finding this versus this, I can actually extract what the mass was. Okay, and this is how we calculate the mass of the proton. Okay, so that's at least a little view of what we do. I certainly don't expect you to understand all the details, but basically we've done this, and so after 30 years we actually get to this plot here, which is from this science paper, where we look at the spectrum of various different states, so the mass of various different states, I should say. So here is the neutron, and the blue point corresponds to the lattice QCD calculation, and then the white lines correspond to the known experimental values for these masses. So we have the neutron, but we also have the lambda baryon, the sigma baryon, the cascade baryon, some other stuff, and some mesons down here. And you can see that these calculations are able to completely reproduce experiments here. And so we say we can now calculate the mass of the proton from the underlying theory of the strong interactions. Okay? So this is pretty important, in fact, because previously we had really only verified that QCD was the theory of the strong interaction at very high energies, where we could do these calculations expanding in a small number. But now, this plot here is basically a demonstration that QCD describes strong interactions when they're strong, which is kind of where you want to describe strong interactions. Okay? So this is really the main thing I want to tell you about, is that we really now know that, well, QCD is, at least to the level at which we can test it experimentally and computationally, is right. So there may be things beyond it, but we would need more precise experiments to see differences. Okay? So that being said, now we get to the interesting part. So because, as I said, Chadwick measured the mass of the neutron in 1932. So great, we took a long time to calculate it. There is a clock here. I should finish pretty soon, right? Yeah, okay. So let me just say one thing. I've got a couple of different examples of ways in which actually having the ability to do these calculations and verify that QCD is right, we can actually calculate things you can't get at experimentally. So let me just turn back to this, to the neutron and proton system, and back to the fact that these masses were different. Okay? They're very close to each other, but they are different. The neutron is heavier than the proton, and that actually means that the neutron can decay to a proton plus an electron plus a neutrino. And this is a very important thing. This is basically it's very important for many reasons. So experimentally, we can just measure these numbers, and that's it. Okay? However, these numbers come from two different places. So the proton is on average 2 up quarks and a down quark, and the neutron is on average 1 up quark and 2 down quarks. So the difference in these masses can come from the fact that the up quark is lighter than the down quark. Okay? But it can also come from the fact that the proton has an electric charge and the neutron doesn't. And so having an electric charge means that if you're moving along, you basically have a cloud of photons that follow you along. Okay? And they like to raise the mass of a charged state. So a proton is actually heavier than it would be if it didn't have a charge. Now experimentally, you can't make a separation between these. You can only measure the neutron and proton masses. Okay? However, having complete computational control over the theory that we know gives these numbers, you can actually ask more detailed questions. So this is another calculation very recently of these mass differences. So this one here is of the difference between the proton and neutron. This is differences between other mesons and baryons, but let's just focus on this one here. And the line is again the experimental number, and the green point here is the lattice QCD plus QED calculation. So this is a calculation of including QCD and also electromagnetism. And you see that, okay, well, we verify the experimental difference. But now we can do an interesting thing. We can take this calculation and we can do it again, but not have QED there, right? So we can just have this difference between the masses, but not this piece here. And we can ask, well, of this number of 1.3 MeV difference, what fraction is coming from electromagnetism and what fraction is coming from the difference in the quark masses? Or we could do the opposite thing. We could keep electromagnetism, but make these quark masses equal. They're just parameters in our theory, right? So we can change them. And you could then see what part is coming from electromagnetism. So this is, okay, might seem like a fairly abstract thing to do, but it's actually really important for our existence, in fact. So here I have a plot that shows the fraction, the difference in mass between the neutron and proton coming from this piece of it, and the difference coming from electromagnetism, QED in this case. Okay? And so with these calculations, where we can play with both of these pieces independently, you can actually pin down what bit is coming from each source, and we find that there's a point sitting here. So if we ended up sitting up here somehow, right? If electromagnetism was somewhat weaker, okay, that would mean that the mass difference from QED would get smaller, and so we would actually move up here. And if that happened, well, we'd be in big trouble, because now the mass difference between the neutron and proton would be so small that when we try and do fusion, taking neutrons and protons and forming a composite thing called deuterium from them, releasing energy, that wouldn't happen. Okay. Also, if the other thing, if we made this mass difference smaller, moving across this way, we would move into a regime where we would not have stars as we know them, right? Because hydrogen would automatically would very, very quickly fuse into helium, and all we would have in the universe is helium, and so we would have helium-burning stars instead of hydrogen-burning stars, which would be a very interesting universe to live in, I'm sure. So yeah, these questions of well, what the value of the QED interaction is and what the value of this mass splitting is, they're really important for understanding what the universe could have been like. We actually know now that the universe sits right here and fusion works as it does. That's great. But if it wasn't, we can sort of ask the question, well, why is this value here? And we can ask really quite deep questions about why is our universe like it is? And let me just leave you with one last thing. So to actually understand these questions, you need to do a little bit more than just playing with the masses here. And this is some work that I've been involved in recently. And this is actually trying to understand these fusion processes, where we take a neutron and proton, smash them together, form this thing called the deuteron, which is a bound state of these two. It's basically hydrogen, but with an extra neutron, and giving off energy through a photon. Right? So this is a fusion process. Something similar to this involving two protons is actually what powers the sun. But this process here in particular is critical for the evolution of the universe. This is essentially the first nuclear reaction that goes on in something called Big Bang nucleosynthesis. And if it didn't happen how it happened, we wouldn't be here. We wouldn't form the deuteron, we wouldn't form heavier elements, and we wouldn't form carbon, and, well, we wouldn't be here. So let me finish there, and please feel free to ask questions. Thank you.
Greg, you want the other mic? Oh, here, go ahead.
In these LCD calculations, you describe a lattice. How do you decide on the scale of how small and how far do you go until you say it's
So you can sort of think about it as, okay, we're trying to describe the physics of, say, a proton, right? And a proton, we know, has a size that's roughly 10 to the minus 15 meters. And what we want, in order to sort of describe the dynamics of that system with reasonable fidelity, we need that the discretization scale is very small compared to the scale at which physics is happening. Okay? So that really tells us how small those lattice spacings have to be sort of close to being the right answer. And then what we do is we do calculations for a range of different scales and extrapolate to zero spacing. We also have to think about the size of the space-time. We need that to be big compared to the proton. And this is sort of why the computational cost is so big. We basically have a hierarchy of scales that we need to impose in these calculations. That's not easy.
I have a fundamental question. When you take a quark and an antiquark and stick them in something as small as a meson, what prevents them from just annihilating?
That's a very good question. So quarks come in different types. Okay, so we can think about, like I talked about up quarks and down quarks and strange quarks and things. So if I take two quarks that are of the same type, indeed they can annihilate. Okay? But if I take, say, a up quark and an anti-down quark, then they can't annihilate. Okay? Basically because so what happens if I take say an up and an anti-up, they can basically turn into a gluon, right? But the gluon doesn't carry what we call a flavor quantum number, so it doesn't have any upness or downness or strangeness. Okay, and the strong interaction actually preserves upness and downness. So if I have something that has two up quarks and a down quark, it's never going to have it's never going to turn into something with just three up quarks. It can turn into something that is two up quarks and a down quark and an anti-up and another up, but it just can't do this. So in order for changing flavor, you need the weak interaction, and that's also a very important part of things, but so I didn't get to talk about it today.
I think you mentioned that the quarks were moving at the speed of light in the baryons.
Very close to it, yep.
But don't they have mass? And
so they do.
So how does that work?
Right, very good question. Yes, so the quarks, they have a very small mass. So the proton mass in these units was 938 MeV. Okay, so if we ask what the masses of the up and down quarks are, they are something like 3 MeV for the up quark and 5 MeV for the down quark. Okay, so you can see that two up quarks and a down quark doesn't make a proton, right? It gives you something like 10 MeV out of 1,000 MeV. So those masses are very small, and so yes, they're not quite moving at the speed of light, but they're moving very close to it. Compared to, say, a proton moving, it's very close.
I'm not sure how to ask this. I'm always wondered, how do you know if you keep finding particles inside particles inside particles? Is there? It seems to me that the only way that you would know if you're done is if maybe time is discrete and not continuous. Is there a relationship between that?
Yeah, so the question of when you would know when you're done, I think you can't, strictly you can't answer that. You never know you're done. All you have from experiment is information that in the experiments that I've done, I can describe what I see, right? Now, it could be that there's something much more fundamental going on, but and it's almost certainly the case that the Standard Model is not the final thing. For example, the Standard Model doesn't tell us why neutrinos have mass. It doesn't tell us about dark matter. So there's things that we don't understand. So I would say almost all theoretical physicists think that we're not at the final thing. But for these experiments that I'm talking about here, this theory is really is describing what we see. Okay. And in fact, you should think about what I said about quarks, right? Quarks have quarks inside themselves, right? If you look harder at a quark, you see quarks and gluons inside it. So it's kind of a tautology to even ask what's inside a quark, because the answer's a quark.
But if energy was discrete, could not time be also discrete?
Yeah, so there's many things that could happen. I mean, there are people that think that, in fact, if you go to very, very high energies, so energies where gravitational forces become relevant, then in fact space-time could be discrete, right? And yeah, but to get to experiments that can actually probe that, we need to invent some extremely powerful new technology to be able to do that. So,
a couple questions over here.
Yeah.
What's the difference between like a strange quark and all the other quarks?
Yep. Okay.
Why is it so strange?
Why is it called strange? Yeah. So it's a historical reason why it's called a strange quark. Basically, people looked at these first experiments where they started to see that there were lots and lots of things, lots and lots of particles in their experiments, and they said, that thing's strange. And so they first discovered one of these funny baryons called the lambda baryon, which now we know contains a strange quark. And they thought, well, that's a pretty strange thing. It doesn't behave like the protons and neutrons they'd seen before. So the difference between quarks, different types of quarks, really is two things. Firstly, they have different electric charges, and they also have different masses. So the strange quark is a little bit heavier than the proton, than the up and the down quarks, and the bottom and top quarks are even heavier.
Yes, the graph that you showed, where the little loop in the graph when the quarks are at their closest, minimum energy between them, at that point you can hit them with very high energy and blow them apart?
You can blow them apart a little bit, but then they'll pull back together.
Okay, so no matter how much energy you put in at that low energy state between the quarks, they don't turn into pi mesons or anything.
Yeah, that's actually a very good point. Yes, I wanted to gloss over this, but yeah, what will happen is if you try and pull them further and further apart, there's so much energy stored in this, what we call a flux tube between them, that it becomes energetically favorable to create new particles. Right? So basically somewhere in the middle we'll create another quark and an antiquark, and so these two that were at the end will basically snap together with the two that got created, and you will get back to mesons.
That's pretty weird.
Yeah.
Thank you.
All right, on that note, thanks, Will.
Yep, thank you, and thanks for listening.